Anyway, my presentation today is for the analysis of ethanol and benzene extractive distillation using p-xylene as a solvent in a Cape Open Series simulator. So the basic outline of the presentation is I'll give you a brief introduction about what extractive distillation is, the case study that we are going to do, and what other mechanisms can be applied to the extractive distillation process. A brief theory on what basically extractive distillation is, and the mathematical modeling that we have completed, and that is used in the actual simulation. Then I'll go through the case study. Finally, we'll talk about some results and discuss based on that. Then finally, I'll give you a conclusion, present you the reference list, and of course, my contact will be there at the end. So because this is a conference and lots of people over here are chemical engineers, so I won't really go through what exactly distillation is. I guess everyone knows what distillation is. So I'll directly jump on to what the basics of an extractive distillation is. Whenever there are the boiling points of a few components inside a mixture, when they're very close to each other, it's very difficult to separate them. If we use a simple distillation process, we might require an infinite or very high number of trays, and it might take also a very long time to actually distill those two components, distill the components inside a mixture. So because these boiling points are so similar or very close to each other, that's why we use extractive distillation. It's much cheaper, much faster, and gives a better result as compared to the simple distillation process. Now, inside this extractive distillation process, we use a non-volatile solvent. So what this non-volatile solvent does, it's basically a polar compound, and this non-volatile solvent, it alters the relative volatility of the component without forming an azeotrope with them. Because if it forms an azeotrope down the line, it will be very difficult to separate them. So that's why this forms a non-azeotropic mixture with the individual components, and it basically achieves it by altering the activity coefficient of the individual components. And once these individual components, it forms that interactive mixture with them. These individual mixtures are then further sent down into a different column. They can be further purified, and the solvent can then be separated out from the individual components, and that's how we separate them. And of course, we are not going to throw away the solvent because solvents are expensive. So as a result, we try to recycle back all these solvents into the first column. And I'll show you a small snippet of these two distillation columns. So over here in this figure, as you can see.
Completely fine. Sir, yeah.
Yes.
Yeah, sir.
Is there a problem?
It's okay. The slides are moving, right?
Yes. Can you see them moving? Hello?
Yeah, that's fine. Yeah, we can see it, sir.
You can see it, right?
Yes,
okay.
Yes.
I was actually on the first slide. I haven't moved beyond the first slide. That's why. So it's just the basic introduction. It takes a little time. So anyway, this is the figure. As you can see, we have ethanol and ethanol benzene mixture that we have to separate. And as you can see right over there with this temperature and mole fraction graph, we have an azeotropic temperature right over here, which makes it very difficult to separate out these two components. So this temperature is around 314 Kelvin, which makes it difficult. So at that point, it's impossible to separate these two components. So for an effective extractive distillation, what are the key things which are required? So the solvent present in the liquid phase, that should influence the components in such a way so as to affect improved separation. Now, similarly, the non-volatile solvent, it also has to boil at a higher temperature than the key components. Um, and this is something which I've already said earlier, no easy drop should be produced. Otherwise, subsequent distillation will be very difficult for these components and the solvent. And finally, this is more of an experience thing, that the solvent feed should be placed above the primary feed in a dual feed extractive column. So this basically helps to distill out the lighter key components, while the bottom components which are there and which react with the solvent in a different way, they will consist of a mixture of heavy plus a heavy key component and the solvent. Now, what are the basic goals, and how do we go about this entire process? So the basic goal of the research paper that I'm writing, and specifically this presentation, we have to simulate an extractive distillation process. Then just simulating it is not enough. There are investors, because ultimately, what is the final goal? The final goal is to do some kind of a simulation, perform a simulation, and using that simulation, we have to go to the industry, present it to the investors, so that a profitable method of extracting these two components is possible. So only presenting a method is not enough. It is also important to increase the production of these constituents. And finally, while increasing the production, we can also the operational parameters of the system can also be improved, which can be done by improving the separation efficiency. Now, what are the methods that we are going to use? There is a process simulator. It's called COCO. It's Cape Open to Cape Open. I'm very sure many of you must have used them. So it's a fantastic simulator, and it is used to conduct a steady state simulation study. So this is what we have used over here. And then we are also going to use a sensitivity analysis on various parameters. So we are going to change some of the intrinsic parameters of the system, and we're going to find out what the effect it has on the constituent production. Now we move on to the case study. So the case study that I have considered over here, it's a separation of an ethanol and benzene mixture. Now, as I said, the ethanol benzene mixture, the boiling points are very close to each other. As you can see, ethanol is 78 and benzene is 80. So it's relatively difficult to separate out just using normal distillation. So because we are talking about the extractive distillation process, we will be using para-xylene with its relatively highly boiling point of 138 as a solvent in this dual feed distillation column. So by using this para-xylene, what will happen? Benzene and para-xylene, it separates out from the bottom, while relatively pure ethanol will be taken out from the top. And then this benzene, well, let me quickly go through this. This is much easier for everyone. So we have two columns. This is the extraction column. So here we have the benzene plus ethanol feed, and we have the para-xylene as a solvent, which comes out from the top. So this enters from the top, and in this extraction column, it mixes. And the interaction is such that a majority of this ethanol, it comes out from the top, while from the bottoms, we have a mixture of benzene and para-xylene. This benzene plus para-xylene mixture, this is then sent to a solvent recovery column. Now from here, this is a normal distillation process. So benzene with its boiling point of around 80 degrees Celsius and para-xylene with around 138, it's very easy to then separate it out. So then this benzene separates out from the top, while the para-xylene as a heavier component, it comes out of the bottom. It has cooled down to around 100 degrees Celsius, and then is fed back and reused in the extraction process. And of course, some of the para-xylene is always lost in the process. It might be a part of this this benzene or ethanol. So that's why we always have to have a makeup, a very small feed of para-xylene makeup, which can be mixed in a static mixer, and This static mixer has the makeup feed and the recycled solvent, and that can be fed into the extraction column. So now what is the theory behind extractive distillation? So there are two basic methods. The method that we are basically going to focus on is the EQ stage, or the equilibrium stage model, mathematical model that we are going to use. Now, one stage of this correspond to one section of a tray, if it's a trade column, or it can be a typical section of packing, depending on what type of column it is. Now, the basic mathematical model is what we have to do is we have to find out what the measure equations are. So these are the equations for mass, equilibrium, the summation, enthalpy. And because we don't have any reactions which are going to take place, that's why there are no reaction equations associated with the extractive distillation column. So these measure reactions, they are analyzed and they provide the basis for the simulated model. Now, a few of the conditions these are the assumptions that have to be made for this equilibrium stage mathematical model. So a steady state is always reached for a particular tray or packing that we are going to consider. Then the mechanical equilibrium is attained by the system. The vapor and liquid phases of the phase equilibrium, they are assumed to be perfectly mixed, and any heat generated during mixing is neglected, and this is what comes in this enthalpy section. And the only phase reactions, liquid phase reactions, are going to be considered. Any vapor phase reactions, they kind of complicate the equilibrium stage mathematical model, and just to make things easier, we will only be considering liquid phase reactions. Then again, both the reboiler and condenser, they also represent stages of equilibrium. And all stages of equilibrium, if chemical reactions are considered, but since we don't have any reactions, that's why this condition is not really valid. And finally, equilibrium by chemical reactions is not accounted for. Oh, sorry about that. Okay. So this is the mathematical model that we have. So we are going to consider liquid vapor equilibrium stage, where we have the vapor phase and the liquid phase both. So the liquid phase, of course, comes down from the top and goes out of the stage, while the vapor phase rises up and it goes into the stage and then comes out of the top. So the first two reactions are basically the mass balance reactions. So this is for the overall mass balance of the system. While if we consider a component, any component, there can be 2 components, 3 components, n number of components. So the component balance for a component I is this. And again, there are side stream to interstage ratio, flow ratios, which are given by equation number 3. Then equilibrium between the vapor and liquid phases. So this is just the equilibrium relation between the vapor phase and the liquid phase, and this is, of course, K is, of course, the equilibrium constant. And finally, the enthalpy balance across an equilibrium stage is given by equation number 6. So now let's move on to the actual simulation in a Cape open environment. So there are certain conditions that we have to assume at the beginning of this case study. So we will be considering an equimolar azeotropic mixture of benzene and ethanol, which flows at a rate of 100 kilomole per hour at these standard conditions, and it's fed into a 71 tray extractive column at tray 50. And similarly, the makeup solvent of pure p-xylene flows at a very, very low quantity as compared to the overall flow rate of the component mixture, and this is also fed into an extractive column. These reflux ratios, these are just assumed values, but we can always change based on how we want to operate the system. And finally, the product is sent, any bottoms product which are produced, they are sent to a 21 tray solvent recovery column. And finally, this bottom stream of solvent recovery column, which basically is a majority of para-xylene, it is sent to a cooler and comes out of the cooler at a temperature of around 100 degrees Celsius, and then fed back and recycled into the system. Now, after using the Cape Open Simulator, the COCO software, there are a few results that I was able to generate. And after the simulation, so this is just a huge table of all the things that I found. So all the values which are present in bold, those are the results of the simulation, while the non-bold values, those are the feed or the assumed values of the system. So as you can see, for the extractive distillation column, we have oh, sorry about that. Yeah. So as you can see, we have a feed, and this feed, using this feed, we have a distillate, and over here you can see that the distillate is majority of methanol. The majority of it is ethanol, and at the bottoms over here, the majority are benzene and para-xylene. So these are then sent over here as feed to the solvent recovery column, and they become the feed. And from there, after distillation, after the simple distillation, we can see a majority of the benzene separates out a distillate, while a majority of the para-xylene can then be recycled. So this graph basically shows the exact same thing that I've discussed. So if you consider the mole fraction versus stage number of the extractive distillation column, here para-xylene, as you can see, it's at a very high quantity, while benzene is at a very low quantity, but as compared to in the bottoms product, it is quite significant. And then as the stage number goes up, goes higher, we see that the distillate over here, which is the ethanol, it is at a very high quantity. Now, the entire mixture, the bottoms product, are then sent to the solvent recovery column. And as you can see in the solvent recovery column, we have para-xylene, which comes out of the bottom, while benzene comes out of the top and is ultra pure benzene, which can be obtained from this. And there is also a slight ethanol concentration in both the distillate and the bottoms, but it doesn't really matter because it is at such a low quantity. Now let's go through the sensitivity analysis. So at some point of time, we have ultra pure benzene, which has been obtained by the process, and we have a majority of the para-xylene, which has been obtained from the process as well from the bottoms of the system. But then investors, what they look for is they always want to increase the kind of the production of the constituents which are there. So what I did was I applied a sensitivity analysis to the system. And what I did was the makeup supply of the system, initially it was the value that I took was around 10 kg per hour, and then slowly varied that value to see at what point do we get maximum ethanol production. So, and as you can see from this curve, around 31 kg per hour, we can get at a 31 kg per hour supply of paraxylene, fresh paraxylene, we get the maximum ethanol production. Now, even though it might be just 50 kg per hour more than what was there originally in the system, but mind you, this is a 50 kg per hour. So this is a 1 hour production, and refineries, chemical, petrochemical complexes, they run for the entire year. So that's a significant amount of production, a production increase that we get from this. Similarly, there are several cases that I tried for sensitivity analysis. Now, these are only just 2 examples out of those. Then similarly, just changing the outlet coolant temperature. So what effect it has on the ethanol production. So as you can see, the closer the temperature is to a room temperature, or 295 Kelvin, the higher is the ethanol production. So based on this, by just setting the outlet temperature of the cooler that we have for before the paraxylene gets recycled back into the system, we can also, just by changing the temperature of the outlet cooler, we can change the production and increase the production of ethanol. So finally, conclusion. So with all this the case study and the sensitivity analysis that we have done, so what can we conclude from this? So we can have effective Cape open simulations, which can be used to model the ethanol benzene extractive distillation process using paraxylene as a solvent. So this is just one of the cases of extractive distillation. We can have a number of them. What is the economic benefit out of this? Now, so as you saw in the curves and the results, ultra pure benzene can be produced using this method, and a majority of paraxylene can be recovered to recycle back into the system. And using the sensitivity analysis, we can also change a few of the parameters, so that although the paraxylene which was produced in the very end, the mole fraction was 0.93, that can also be increased by changing a few of the parameters. Then, of course, as I said, using sensitivity analysis, it is possible to increase the production by changing systems and some of the operational parameters. And I am still trying to write this paper. I'm still trying to complete this research paper. So in the future, what I have thought is, maybe I would like to investigate the use of some other solvents for better separation of the components. So although paraxylene is one of the components, we can use other polar components, compounds with a lower volatility, which can be used for this specific case study. And I think that's it. So here is my reference list. It's a slightly longer list that I've used. Then, and here is my contact information. So thank you. Thanks a lot for everyone for listening to me. And then if you guys have any questions or queries, feel free to ask.